All right. Hi, everyone. It's 8 p.m. GMT, and welcome everyone to VSA Online. Happy to see you all back again. So today I'm very pleased to have Alex Ellery with us, who will talk about VSA and its application to interstellar missions. So without any further delay, Alex, floor is yours.
Okay, thank you. I'll just share my screen. And okay, so thank you for inviting me to talk to you. I did have a look at some of the talks on the VSA online website. This is going to be very different because I'm not going to talk too much about VSA. I'm going to talk more about the context of where I envisage VSA being useful. And in particular, I'm going to be talking about some of my work and how interstellar flight interstellar missions is basically derived from a lot of the work that I do. My background is space robotics, on-orbit servicing using manipulators, planetary rovers, that sort of thing. And about 10 years ago, I I moved into something called in situ resource utilization, which is for NASA E's uh, for space mining, moon mining, and that sort of thing. And so when I talk about interstellar missions, it's going to be very much derivative from the work that I've been doing. This is the kind of thing that we've been working on. Uh, the idea is to utilize the resources of the moon, build machines that can mine the moon and then process that material into something useful. One of the things I'm particularly interested in is how do we do this at low cost? And of course, sending all this infrastructure to the moon would be very expensive. So one of the techniques I've been working on is an attempt to figure out how to build a self-replicating machine that we can send to the moon and then build up an industrial infrastructure very quickly and very cheaply. So moving to interstellar missions, probably the most famous interstellar mission concept was that performed by the British Interplanetary Science Society in the 1970s, called the Daedalus Starship. It was a two-stage flyby mission of Barnard Star. Barnard Star at the time was thought to have possibly have planets around it. We now know that it doesn't. So they would have headed off in the wrong direction, but never mind. So it was basically the the propulsion system was to use deuterium helium-3 nuclear fusion in a pulse propulsion system to basically accelerate to 0.12 C and thereby cover that distance in about 50 years or so. There have been subsequent to that, there have been other ideas to actually, this was originally a flyby. If we added the third stage with much mass increase, we could then decelerate for an interception mission to any other type of star system. More modern thinking has moved away from nuclear pulse propulsion towards what is known as laser-propelled light sails. The idea behind this is you have a phased laser array. One possibility is the free electron laser. One of the advantages of the free electron laser is that the laser emission frequency is tunable from X-ray all the way to microwaves. The advantage of light sails is that it requires no propellant. You don't have to take the propellant with you. And Robert Forward in the 1980s, I think it was, or maybe, yeah, the 1980s, I think, developed a concept of a light sail which could decelerate at the target. What you're trading off against with something like Daedalus with these kind of these light sail concepts is that you require very, very large sail areas and also large diameter Fresnel lenses to focus the laser light from Earth orbit out to interstellar distances. And this is kind of similar to some ideas that have been proposed today for a solar shield to be placed at the Sun-Earth L1 point to basically refract solar energy away from Earth to reduce global warming. Now, obviously, these large scale kind of engineering concepts are fantasy today. But if we can develop self-replication technology, they become viable. So, okay, let's look at the various types of missions we can imagine. Well, there are three types of interstellar mission. The first one is the flyby. I've already mentioned this, and so we got the breakthrough Starshot, which has recently been cancelled, but was an idea for a few years to use again laser-propelled light sails, all the way to, and there are various. I mentioned Daedalus as one, but there are also various other kinds of approaches to interstellar flybys. As I said, if you can add, say, a deceleration stage to either Daedalus or the laser-propelled Starship, we can then employ the second type of interstellar mission, which is in situ exploration of that extrasolar system. This kind of makes sense to enable this kind of capability because we could slow down and survey an interstellar, an extrasolar system to observe whether the various planets that they have, and also to perform astrobiological surveys. And the third type I've divided to two parts. First one, part A, is if we encounter some kind of extraterrestrial intelligence, and the second part is if we encounter some kind of extraterrestrial artificial intelligence, and the way in which we would interact with those would be very different. But all of these types of missions involve a 50 to 100-year transit phase, and so this is what I'll focus on for the rest of the talk. So if we look at the kind of environment we're going to experience as we go out into interstellar space, well, the first hazards we're going to encounter are going to be the Kuiper Belt and the Oort cloud. But these are very diffusely distributed, so they don't really present much of a collision hazard unless you're very unfortunate. One of the most dangerous and difficult challenges are traveling at high velocity through dust and gas. And this, of course, can be mitigated. Most designs of interstellar spacecraft involve mitigating this by using an erosion shield. We also have exposed to high energy galactic cosmic rays. And one of the approaches, and again, I'll come to this a little bit later, could potentially be mitigated by adopting vacuum tube based electronics rather than solid state. And we could potentially also, common on spacecraft, we use EDAC, error detection correction coding, when we employ memory. The 100-year Starship project run by NASA quite a few years ago now suggested using FPGAs and exploiting their reconfigurability against damage. So when we come for these long duration lifetimes, these long duration missions, one of the problems we encounter is a traditional approach to spacecraft reliability is to use components of very high reliability, which are very expensive. They have a bathtub failure rate distribution. They have high infant mortality, high salinity, but this flanks essentially a constant random probability of failure, which is usually quite low. And again, I mentioned the NASA 100-year Starship study. Their approach was to use high reliability components, which I said is a standard philosophy in spacecraft engineering, and using multiple hardware redundancy, which is also a standard approach in spacecraft engineering. What was new that they were proposing for that study was this idea of evolutionary hardware, where FPGAs would be programmed through genetic algorithms. So there's a diminishing return on redundancy. So what we need to do is broaden the way we look at this by looking at the concept of availability. And as you can see there, availability is defined by this fraction, and the terms are mean time before failure. That is a measure of reliability. So this is the traditional approach. But there are other factors there as well. Mean time to repair is a measure of maintainability. So this implies that if you have some form of onboard servicing, you can reduce that towards zero. And of course, the third one is mean time for supply. This is a measure of logistic supply. And of course, this, again, if you have parts, or you can either have a set of parts, spare parts, or you can manufacture them on board on an as-needed basis. And what we're aiming for is for availability to be one. So we have perfect availability. And this this essentially renders the reliability aspect irrelevant. So we want to focus on maintainability and supply. Now, the Daedalus starship actually anticipated this and was basically supported by several what they call wardens. These were free-flying servicing robots, similar to some of the free-flying servicing concepts that we see today, that I worked on actually during my PhD. So the lessons from space servicing are that we need to standardize our interfacing of modules. We need to define mechanical, electrical, optical, thermal interfaces. And in fact, this is actually a big move in Europe at the moment. The European Union is pushing for a new concept in spacecraft engineering, which is basically a series of boxes. And we basically plug these boxes together to create a reconfigurable spacecraft. This also simplifies the robotic handling, because if you have standard interfaces, you can design your robotics to simply change those modules in and out as needed. So this assumes that we have some kind of stockroom of pre-manufactured modules to allow replacement, but this isn't realistic for a Starship. So if we want to have full availability in a Starship, we have to design it for self-repair. And for this, we need a full self-manufacturing facility on board, so to allow it to replace any component on demand from a limited set of feedstock. And this will apply to any interstellar mission. So it is crucial to minimize if we want to have feedstock, we need to try and control the range and the amount of feedstock we need to maintain that Starship. And this is where demand-like concept comes in. I'll talk about that a little bit later. But there are 7 basic subsystems on board a spacecraft. I'm not going to read through the list, but in essence, about approximately 10 basic materials can supply the full functionality for all the subsystems of a generic robotic spacecraft. So we need to have, and in addition, any kind of onboard fab lab must be able to manufacture the feedstock into the replacement components, including for itself. So it has to be able to self-maintain. This is the demand-like concept. So this is actually derived for the moon. This is we've been working on lunar applications. So on the left-hand side there, you see the functionality, the functional systems or functional capabilities you need to build any type of spacecraft. And on the right-hand side, you see the materials that we could extract from the moon to actually implement those functions. And as you can see, it's a relatively small number of materials we can utilize to achieve this. And I'm going to focus on just one. This is the industrial ecology. Again, this is for the moon. I realize this is a very busy side, but this basically implements a self-recycling, interconnected industrial ecology, which takes raw materials from the moon and cooks them in various ways to yield various products that we need to implement our demand-like system. So the idea behind the Starship is we store metals in oxide form. We do this because metal gets tarnished over the long term, so we keep it in oxide form for long-term stability. So we'll look at alumina for the moment. Alumina itself has physical properties second only to diamond. It's refractory, it's chemically inert, it has high hardness for tooling applications. It can be an additive to composites. For example, we can manufacture cermet, which has high strength and high temperature tolerance. And finally, we can reduce alumina directly into metal aluminium metal using a technique called FFC molten salt electrolysis. And we've actually done this in the lab. We've taken what was originally lunar simulant, Highland simulant specifically, was very rich in a mineral called anorthite. We separated out the anorthite, and then we processed it using HCl leaching, and that created alumina and silica. And we then subjected that alumina to molten salt electrolysis. And what we yielded, and so this shows you the setup in our lab. We recovered we extracted 11% of the mass we actually extracted from the original LHS1 material. 11% of it was aluminium, and actually this is close to the theoretical maximum of 14%. And so carbon monoxide and dioxide were involved at the inert our anode. Yeah, so that was because the anode was graphite, which combined with the oxygen from the reduction process, but we could potentially replace this with a non-eroding anode to get pure oxygen. And in fact, we are currently working on a project called Oxygen, which is funded by the UK Space Agency. We're working with US and UK partners to build a lunar payload, which includes the molten salt electrolysis unit, which we're building to reduce lunar regolith directly to recover oxygen. So we're currently working on that at the moment. So once we reduce this to aluminium metal, in fact, aluminium constitutes almost half of the inventory of a spacecraft material. So it's a good starting point. Aluminium itself is a multifunctional metal. It's highly versatile. It's a good, again, I'm not going to list the things it can be used for, but in particular, it can be used as an electrical conductor. And it can be, and of course, it's used widely as a lightweight structural material. And by focusing on just a few other additional resources that we can extract from the moon, we can start to create a range of different alloys. So I'll point you in particular to aluminium 6061. This is a widely used alloy for various kinds of applications. And so we can potentially extract silicon and magnesium from that to get the vast majority of the if you look at the copper and the chromium that I've struck out there, that usually is added to 6061. But the chromium we can omit because the chromium is added to render the aluminium robust to corrosion in wet oxidative environments, which don't occur on the moon. Copper is usually added to add some kind of malleability to it, but we can engineer around that issue. Aluminium itself is still pretty malleable. And there are various other alloys we can make, for example, alnico, which is a permanent magnetic material, which is basically almost as good as rare earths. Once we'd done that, we had converted our aluminium metal that we extracted from the molten salt electrolysis unit, and then we drew it into wire, and the wire was then added as feedstock to a 3D printer called an electron beam additive manufacturing unit, and we 3D printed this into a representative basic cylinder to represent some kind of cryogenic tank for holding liquid oxygen or liquid hydrogen. There are other possibilities as well. For example, the molten salt electrolysis technique was invented primarily to reduce titanium, rutile that is, into titanium metal. And this a company called Metallysis in the UK has actually demonstrated this and then 3D printed the result into parts that you see there, using a laser printing rather than electron beam printing. So one of the things I've been interested in is how far can we push 3D printing? Is it actually a universal construction mechanism? And the answer to that is maybe. So if we've been looking at self-replication, as I said, On the right there, you see the RepRap 3D printer, which can print its own plastic parts. And if we wanted to convert that into a full self-replicating machine, we would then have to be able to print the metal bars. We'd also have to be able to print the electric motors and the electronics and the computer hardware and software. We will talk about the latter three, in particular the latter two, a little bit later, but the electric motors I'll talk about in a moment. But the idea of this is that if this is a universal construction technique, a universal constructor is essentially a kinematic machine. It can manufacture any other machine given the appropriate resources of materials, instruction, and energy. And this includes potentially a copy of itself. And this is from the original von Neumann idea that a self-replicating machine is basically a subset of the universal construction method. We can adapt von Neumann's technique, or ideas, should I say, to unstructured environments by building a suite of kinematic machines. And so all machines of production, all kinds of machines that we can build are in fact kinematic machines. And what a kinematic machine is a specific kinematic configuration of electric motors. All robotic machines are in fact kinematic machines. So if we can 3D print electric motors, sensors, and control electronics, all else will follow. So if we can 3D print motor systems on board, we can then, in theory, print any kind of manufacturing machine on board on demand. And in fact, this one of the things we've been doing was to actually demonstrate that we can, in fact, 3D print an entire motor. And this is what we printed. It was assembled by hand, but each part, every single part of it, was actually 3D printed using different 3D printing techniques. So the idea behind this was to show that complex machines can be 3D printed. So let's go to the electronics. Well, as I alluded to earlier, we've been looking at vacuum tubes, and there are various reasons for this. The primary reason is that trying to build a solid-state electronics foundry on the moon or on board a spacecraft would be extremely difficult. Solid-state manufacture requires a lot of different chemicals and a lot of different processes, which are very, very complex. So this is not really suitable for manufacturing electronics. Vacuum tubes, on the other hand, are relatively simple of construction, and they're potentially printable. So they're thermionic devices where we can use a limited set of materials. So we can use Koval resistance wire. We need a tungsten cathode coated with something like calcium oxide and alumina, which I missed out there. And we can use nickel electrodes. And this can all be placed into an evacuated glass envelope. And all these materials are derivable from the lunar resources. So if we look back in time to Colossus, which was built at Bletchley Park, it comprised 2,400 vacuum tubes, actually designed by Tommy Flowers, who is a very underappreciated engineer, who I think deserves greater recognition. He tends to be paled by Alan Turing. But the problem we have is that if we start to build the kind of modern kind of CPU designs using vacuum tubes, so if we look at ENIAC, for example, 17,000 vacuum tubes occupied a very large room, we would have any kind of like modern CPU be just too ginormous to build. So maybe CPUs are not really the appropriate architecture for building a vacuum-based computer. So we've been looking at neural nets. So there are a couple of approaches we can use. One is, instead of trying to build a general purpose computer, we can actually implement specialized circuits which are distributed. And so this is inspired by octopus brains, which basically the octopus has 9 brains, 1 in each arm plus a smaller one in the head. So potentially we can actually implement a level of intelligence using specialized circuitry, a distributed set of specialized circuitry. The other advantage of neural nets is the software is built into the neural net architecture as the weight matrix. And finally, the complexity of the network grows logarithmically with task design. So we can potentially keep control of the footprint of the neural network. So what we're interested in is implementing neural nets in hardware. And this is what we've done. We've used a modified Yamashita Nakamura printable neuron. It has fixed synaptic weights. And as you can see, it comprises only just a few different simple circuit components. And this is our modified version. It's basically a McCulloch-Pitts neuron. And we implemented 2 of these. And we put them onto this rover and this little desktop rover. And just 2 neurons, it implemented fairly robust obstacle avoidance behavior. So there's no microcontroller or anything else like that on there. The reason why it jerks like that is because it's to do with the capacitors, and we couldn't be bothered to smooth the capacitance. But anyway, it illustrates that you can get Bratenberg BV3 type level behavior using just 2 neurons. So beyond that, we decided one of the problems we had is that if we 3D print kind of neuron circuits, one of the issues that's going to arise is the problem of tuning. There are going to be hardware variations, and so like if you try to print like a particular value of resistance, that's going to vary over a degree. And so we're going to need to have some kind of means of learning to fine-tune the weights. And in fact, I had a student from India one summer and discussed with her how we might be, whether it be possible to build a backpropagation algorithm in circuitry. And lo and behold, this is what she managed. And on the right, top right there, that's the forward circuit, and on the bottom right, that's the backpropagation circuit. So we were able to implement the backpropagation algorithm in circuit form. And this is it actually in action. Again, it was basically trained just to do a simple stop when it came to an obstacle. And so, yeah, we're very pleased with this, that we managed to achieve this. The weights can potentially be updated, but not the topology. And this actually imposes limits on the learning, which potentially is an advantage, which I'll talk about a little bit later. So one of the things we want to do next is to convert the analog neuron into an analog spiking neuron. What we're going to explore initially is by using a fairly simple approach, which is by adding a Schmidt trigger. One of the things we're concerned about is like trading again the footprint of the circuitry against the complexity of the behavior of the circuitry. There are a couple of other things we want to explore, including things like implementing Kalman filters in neural net form, but I won't talk about that now. So going back to our Starship, well, the requirements are to implement failure detection, isolation, and recovery. Now, we can do simple things like simple fault diagnosis through large data sets, but multiple faults, if they are related to a single cause, can often propagate through the system. This happens on spacecraft all the time. When we upload software workarounds, quite often what happens, there's a cascade effect of failures occurring subsequently through different systems, particularly as the mission profile changes. Often for more complex faults, Kalman filters have often been adopted for fault isolation, for detecting there's a fault and then isolating that fault out of the system. But more complex faults, which can potentially have exponential different configurations from multiple causes, require some kind of reasoning capability. So full recovery is going to be the challenge, and this is the realm of repair. Now, repair involves intense interaction with the physical world. It involves chemical processing, manufacturing, assembly, integration, the diagnosis of faults, planning manufacturing schedules, conflict resolution, Bayesian interpretation of data, pattern recognition, etc. We need the whole kit and caboodle of AI in order to implement a robust system capable of self-repair on the Starship. So we need some kind of hybrid AI approach. We need symbol manipulation for reasoning. We need neural nets for pattern recognition. We need Bayesian methods for handling uncertainties. We need physical grounding as well. And we also need the ability to learn. I'll just mention some work we did a few years ago. This is, I'll show you here, one of the problems we have with training robotic machines on Earth is that when they apply to space, the dynamics becomes very different. Well, I say very different. It has the same basic form, but because we no longer have a fixed base, we have a moving base, and that dynamics has to be incorporated into the control system. And so one of the things we were looking at was transfer learning, a neural net which had learned a forward model of a manipulator, and then adapting that to the space environment. And we found that, so in effect, it was modeling what astronauts do, essentially the cerebellum of astronauts and how they adapt very quickly to the space environment. We found that, in fact, the neural net couldn't learn couldn't learn to adapt to the space environment. So there are limits on what the neural net is capable of learning, or at least transfer learning into a new environment. So even though the underlying dynamics have the same form, it was unable to learn from the new input-output pairs. So from earlier, I started looking at neurosymbolic processing, because it seems to me that we need to have some kind of symbol processing, but also some of the advantages of the neural networks, their ability to learn and so on. And of course, the Bayesian brain is another kind of approach. Well, not inconsistent, but another approach which looks at how the brain functions as a Bayesian system that mediates between a top-down model and a bottom-up sensory system. When I think of that, I immediately think of Kalman filters, because that's what I'm most familiar with. In terms of, because Kalman filters are in fact a specific rendition of a Bayesian system. So neurosymbolic approaches, we map symbol representations into neural networks, and there are three basic approaches. We map rules into the neural net, and there are various examples of this. The K-band, fuzzy neural nets, Markov logic networks, and so on. And there's a second one which I haven't really looked at in any detail, based on the restricted Boltzmann machine. And the third one is where we embed logical rules into some kind of tensor representation, and this is where the vector symbolic architecture comes in. So the way I see this, I think the VSA technique is extremely promising, where we can implement symbol manipulation in the neural network. And why I'm particularly interested in it, because it ties in very nicely with what we intend to do, which is to start building spiking neural networks. And what we'd like to be able to do is to incorporate some kind of AI-based symbol manipulation to those networks. Now, in a broader term, what this provides us with the ability to do, and I think this is very important from the point of view of having an AI on board an interstellar starship, is that we can pre-program the neural nets with prior knowledge, and that prior knowledge will shape its future learning. And so it ensures that its learning is bounded. And I think this is very important from the point of view of when we send out robotic envoys into interstellar environment, we actually employ some form of control over it. And this actually, by limiting its learning trajectory, potentially this provides a form of learning, of remote control. So I think there are various issues. I mean, one of the reasons why we want to do spiking neural networks, because they tend to be a little bit more biologically representative. When we want to explore the distributed intelligence concept with multiple specialized small neural networks. And potentially, I think a rather enticing idea is that given the neural response times and reaction speeds, this suggests that cognitive tasks that we're capable of have less than 100 neural steps, which suggests that potentially we can build symbolic systems which are again have a relatively small footprint. So I think VSA offers enormous promise for implementing symbolic capabilities to spiking neural nets. We need to have learning, but that learning has to be directed through prior knowledge, essentially pre-programming. We need to ground those symbols into robotic systems that interact with the real world. And there's also an interesting facet to this, in that if we are interested in implementing human level intelligence, the question then becomes, is human intellect or human reasoning actually logical and Bayesian? And there is evidence to suggest that it's not. For example, the Watson selection rule and prospect theory is also based on that our risk aversion tends to skew us away from Bayesian behavior. And I'll leave it there. Okay, thank you for listening.
Alex, thank you very much. This is very insightful talk. So it really awakes thoughts about how to construct new computers for interstellar missions. So let me open the floor for questions. So let me bring up the list of participants. And maybe while people are a little bit shy in the beginning, so I have a couple of questions of my own. When talking about the self-replicating machines and the specific computer architecture that you're developing, how, I mean, are there any theoretical estimates how powerful, computationally powerful they can be? I mean, given this size, the physical size
Well,
of parts?
at the moment we haven't defined any physical size because we haven't explored it enough yet. We've built 2 neurons. What we want to do is build more and more neurons. We did some simulations where I think we had about 20 neurons and implemented what's known as SLAM. So this is called self-localization and mapping. Sorry, simultaneous localization and mapping. So the idea is that we could navigate any kind of rock field or anything moving around fairly robustly. We were actually doing this for Mars, actually, more than anything else. So potentially, it depends on what you want to do. I don't have any insights yet onto how big or how many neural nets we will need for the complete system. Until we've defined the system in more detail, that's going to be something in the future. We don't know what that will look like.
So I let other people. Thank you for this answer. So I let other people to ask questions, and then I have a couple of on my side as well. So Adam, please.
First of all, thanks for your presentation. That was very clear. If we go back all the way to the premises, I think there was this counterintuitive point where we want to carry raw materials, where the kind of classical frame of thinking is we want to pack as much very high tech things in there as possible, where the reasoning is you can use a circuit board as structural materials, but you cannot use structural materials as a circuit board, right? That is a general thing. So what is your intuition that these raw materials, like, is there some kind of recycling that you have in mind? Is there some kind of circularity that I'm missing there? And then I
Yes.
have a second question about AI, but please go.
Yes, I think if I understand your query correctly, um, yes, we want to keep it simple. So one of the constraints of most of the constraints that I employ are employed either with the resources we have available to us, or it's an imposition by a self-replicating machine. So imagine you have a mobile phone in front of you. Now, in that mobile phone are probably about 40 different materials, 40 different elements, which are done in various combinations and so on. Now, in order to manufacture that mobile phone, you have to, each material has to be mixed and then chemically processed, mined, all the way back to mining. So all the machines that you need to mine and then process that material and then configure it and then build it and then manufacture it, and they all have to come together and then be assembled into the phone. So you have this massive fan-in of infrastructure that's needed to create the mobile phone. Now, create many of them, so it's worth that infrastructure. But with a self-replicating machine, you have to narrow that fan-in as much as possible, which means you need to minimize the number of materials you need, which minimizes the amount of mining machines you need. You need to minimize the chemical processing, which again, what you're trying to do, you're trying to minimize the footprint, which then has to be manufactured by that system. So in order to close that recycling loop, that self-replication loop. So we have a vested interest in trying to minimize the sophistication of the system, our self-replicating system. And this is actually quite difficult to do because we also have to think about how does it generate power and so on and so forth. So we adopt some biological methods, so inspired by biology. So, for example, you may be familiar that feathers, for example, were originally evolved for thermal insulation in dinosaurs and birds, and then later adapted for flight. We do the same thing. So what we want to do is we want to use certain components, and we want to use them for many, many different things. So, for example, the vacuum tube. Well, we can use that for electronics, for data processing. We can also use that for conversion of heat energy into electrical energy. We can also use it as an optical sensor for cameras, arrays of camera arrays. And similarly with motors, we can use the motors are typically used for actuation, but we can also use them for power storage, in flywheels. So what we're doing is we're taking specific components and then adapting them for multiple different functions. So that's the approach we've been taking. Does that answer your question?
I feel like it addresses okay, it addresses the part of, like, all right, circularity is indeed easier if you can, if you are working with these more raw materials and the simpler components, and the reuse on the simpler components kind of makes sense. That specialization may stand in the way of the reuse of the components. So I guess, like, just from a mass perspective, for example, the like for one for one tube, you may be able to carry 15 chips, which you can like use one after the other, which is a huge ratio to in the mass, and then maybe self-replication isn't the goal, but self-replication was just like, how do we make these 100 years, or how do we make these 1,000 years, and not the goal in of itself. Anyways, for the AI question, I feel like this is as you point out, like a quite complex challenge, and to me that starts with an architectural design and the requirements of what is it that you want from this, and then try and like lower that further into the technology, because I feel like this is quite close to state of the art in capabilities. While like if you look at up until SpaceX decided to just like put i7 processors in orbit, like they the compute capability of these hardened processors was 25 years behind on the
Yep.
on the state of the art. So I, I I feel like marrying these two desperate um, fields of state of the art AI and autonomous control. You gave the example of robotics, where the state of an art in robotics is actually not very far, right? We are not able to do that much autonomously. So to constrain yourself in looking at what platforms there are to host these behaviors on, while the behaviors themselves like need to be beyond state of the art, seems like a hard challenge to me.
Yeah, this goes back to your earlier point about why not ferry all your chips to where you need them, either on an interstellar spacecraft or onto the moon if that's where you want to go, and that's a fair point. There are a couple of issues, and that is, yes, you can ferry a bag of computer chips with you to replace, but there is a cost to that, and the cost to that is it's not just it's not a shopping basket. It basically has to be maintained under controlled conditions. It has to be protected from the environment because the space is a radiation environment. Um, And so, yes, I am limiting myself, but at the same time, my approach, my philosophy, as it were, is to go against the traditional spacecraft engineering philosophy, which is to basically come up with an architecture and then flow down. What I'm doing is the opposite way. I'm trying to build from the bottom up, and in a way, what we're trying to do is we're trying to do what must have happened during the origin of life, or life emerged from simpler components. And somehow some of those, and they all came together in some fashion, but you needed the original components, certain capabilities before life could have emerged. If you look at the biological cell, you got things like ribosomes and so on and so forth. Uh, there had to be some kind of capacity in order for life to emerge, with these prior capabilities. And so what we're trying to do is we're trying to build those prior capabilities from the ground up. And then later on, once once we've got the basic functionality, then we could start to put together into an architecture. Does that make sense to you? I mean, the other thing is that from a purity point of view, where do we stop? Where I'm interested in creating something that can self-replicate. I could say, oh well, that's an exception. I won't do computer chips because that's too difficult. I don't want to do that. I think that we have to do it in such a way that's consistent, and it wouldn't be a self-replicating machine if the brain part wasn't part of the self-replication system. Plus the reliance on vacuum tubes, they're much more reliable in the vacuum in the radiation environment than solid state. So I think in the long term, there are other techniques. For example, there are some solid state techniques which actually NASA's been working on a vacuum tube which is very tiny as a micro technology. So yeah, I focused on the approach of using vacuum tubes mainly because A, reliability, and B, it fits in with the self-replication scheme. And I'm committed to that.
I I have a couple of questions in the chat. So I think they two can be combined somehow. So first, maybe more VSA related. And speaking of vacuum tubes, so the question from Tyler is how exactly would data be handled and stored? So if your team explored analog representations and computing of HGC BSA itself, and maybe connecting the previous question from Antonella, whether this approach, I mean, the philosophy that you described, is applicable, or do you think if it is applicable for onboard satellite intelligence?
I didn't quite get the first one, but the second one I can answer straight
So
away.
the first one was, I think, about the so it's a technical question on how VSA operations would be implemented on the type of hardware that you envision. So having vacuum
Sorry.
tubes and such.
So
Like VSA vector operations.
oh, right. Okay. That's actually that would be a question I'd ask you. I would ask you guys, how could we do this? And in fact, that's a question of which I have no insights. So how would I implement VSA on the analog circuitry? I don't know is the short answer, and I was hoping you could enlighten me on how that might be achieved.
Okay.
To your second question on is this applicable to current satellites? I would say yes. One possibility is we could print circuits, with multifunctional structures, for example, we could embed circuitry into the structure of the spacecraft to come up with new designs of spacecraft, for example. So yes, we could, CubeSats, this would be ideally suited to things like CubeSats, this type of approach. Because at the moment the behaviors are relatively simple. So we could basically build neural circuits to implement relatively fairly simple control systems for CubeSats, for example. So yes, that's definitely applicable.
Okay, thank you. So let's see if we have more questions from the audience. I have a question, or maybe it's not even a question, it's more of a reflection, after listening to your talk. I mean, when you describe the whole process of this circular production, so it appears to me that it involves quite complex knowledge representation and reasoning in order to, enable all this self-replication, to understand which parts can be produced from
Yeah.
what parts. So the machinery that does this inherently should be rather complex and sophisticated, so way beyond two neurons, so to say. And again, so I just want to link to my previous question. So to me, somehow, I mean, in this very specific use case, the question of computing capacity somehow also relates to physical availability of resources and physical space. I mean, how much space.
Sure.
So, but as you said, so probably nobody was thinking about this along these lines. So how
No,
many? Yeah.
which is why I discarded the CPU idea, because assuming we're wedded to vacuum tubes, the CPU becomes unmanageable. So which is why I went with the neural network kind of architecture, because it seems to me rather than trying to build a general purpose architecture, what we can do is build specific neural nets for specific functions and then plug them all together. Whether that would work or whether you get conflicts or not, I think only we would have to see about that. But certainly, being inspired by something like the octopus or even the human brain, there's an idea that the human brain comprises lots and lots of modules which happen to interact with each other. And again, each module is a specialized type of computational system. And I don't know, the human consciousness is some kind of emergent phenomenon. which arises out of it. So again, there's no I don't see any reason why we can't have individual computational modules which perform specific functions and they work together.
Fair enough. As I said, so it wasn't a question, more of a reflection. So Tony, so I
Sure.
see.
But the short answer is, can that work? I don't know yet. But
Yeah, absolutely.
in terms of there's no reason why it should not work. At least
But
I
the
can't
whole
think of one.
concept is very intriguing. Absolutely.
Yeah.
Tony.
Yeah, where do you think the bigger challenges are? I see sort of two distinct aspects to the problem you're trying to solve, which and one is the physical componentry that you use, and the other is the computational control mechanisms for
Right.
that. And you've got it sort of feels to me like the bigger problem to solve here is actually the physical components that can work. And I'm just wondering, and once you have that, then that gives you the materials that you can build your computational system with. And I'm just wondering, what your views on that are, because one thing I was sort of thinking about as you were at the beginning of your talk was, okay, this is a very interesting computational problem. Could we create a toy environment where you could have, where people could experiment with computational control for it? But then, as your talk went on, I see how important the physical constraints are, and it sort of feels like we don't yet know enough about what's possible and what can be accomplished and what the constraints are there, the actual physical things that you build with. It's very interesting that you said that the vacuum, that you see vacuum tubes as the most promising approach here. There's obviously there's at least three different computational substrates you could have. It's solid state vacuum tubes and good old neurons, biological neurons, which also come that those are a self-replicating. The whole biological system is obviously a self-replicating machine that accomplishes both mechanics and computation. So yeah, interested in where you see sort of the most important constraints and problems.
Sure. I mean, you're absolutely right that obviously the component level is what's going to determine our ultimate capabilities. And in fact, that's why we're focused on the components primarily at the moment. We're focused on, the vacuum tubes. Can we build vacuum tubes? In fact, we're actually 3D printing magnetrons, which is a type of vacuum tube at the moment. The cathode part is the most difficult part to print and manufacture, and we haven't yet managed to achieve that. But as I said earlier, we're focused on trying to do everything bottom up, and so we're focusing on the individual components and trying to get that right first before we start to put it together into something like more into an architecture. So I think the architecture, you're right, will depend critically on what we can do with the individual components and how we can configure them. There's another part to your question. What was that? There was another part to your question, I think.
Yeah, sort of whether it's at a stage where you could actually create like a toy environment where people could experiment with the computational controls, and learning
Right.
mechanisms.
Well, in a way, we're doing that already. So we're actually using op amps, which are basically built with transistors in them. So we haven't yet, so we have, because we haven't got the vacuum tubes yet, we're still playing around with building neurons out of traditional op amps, which are built with transistors, in order to examine the architectural aspects. So far, we've only done 2 neurons, but eventually, I think we got kind of waylaid with the back propagation algorithm part, and so we've concentrated on that rather than building more neurons. Maybe that's something we could do in the future. The second part of your question was, you mentioned We've got vacuum tubes, we've got solid state and neurons as well, biological neurons. That's an interesting idea. I've been quite resistive to the idea of actually incorporating biological components into this. But more recently, I've started to open up my mind to this idea, primarily because we've actually started looking at using extremophiles to extract tungsten uh, from minerals, and so I'm more conducive to looking at adding a biological component to a self-replicator, though I'm not really clear how we might be able to do that because it involves a whole new set of materials. We have to have organic material. On the moon, of course, it won't work because there's very little carbon on the moon. So there's very little in terms of resources there. We would have to bring things like carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, and so on, to the moon with us. And the same applies if you're going in a starship. You'd have to have some kind of biological. You'd have to have material in biological form that could then be metabolized and then, converted into a cellular self-replicating system. So it would actually operate independently of everything else, I think.
Right. Yeah, you'd also, yeah, like you're saying, whatever systems, they have to be robust to harsh environments like cosmic
Yeah,
radiation and
yeah,
yeah,
and tissue is not very
yeah,
robust.
yeah. Okay,
Yeah.
okay, interesting.
There is a follow-up comment from Tyler. If you can read in the chat, or you, Tyler,
Oh,
can enable your mic and
where's our chat? Okay, yes.
yeah. So there are approaches that are compatible with wave systems, such as vacuum tubes. So the question is
How
how
data is
data is
stored.
stored.
Right. Okay. Yes. Yes. We've been looking at magnetic core memory because magnetic core is basically made out of the same components as a motor. You got magnets, you got wires, and things like that. So we have looked at the possibility of implementing magnetic core memory because it's made out of the same materials as motors and wires and so on. I'm aware that the problem with that is that they're fairly chunky, and I haven't resolved that particular issue. We haven't looked at the numbers, to be perfectly honest. We need to know the amount of memory we need to specify the machine and how much memory that's going to take. And also, we also have to add robustness to it by adding error detection correction coding to it as well to ensure that as it's copied, there are no mistakes in it. One of the things we don't want is evolution. So we want to ensure that no evolution occurs from generation to generation. So it's basically under control. Does that kind of avoid your question?
Yeah, boy, yeah. Okay, okay. Good. Listen, I think we had a great discussion. So thank you all for Jill. So you are
Yeah.
unmute your mic, please.
Am I online?
Yes.
Yes, I can hear you.
Good. One of the things you're going on interstellar and you're needing to communicate probably more than you understand right now would be my guess. And that's going towards entanglement, which you're leaving kind of, it's not behind, but that's probably what will be the communications medium. And it's left me foundering, thinking about if I had to write this story, how's it going to go? Can you respond to that?
Yeah, I'm aware of quantum entanglement as I think they're being tested in spacecraft as we speak. Um, I'm not enough of a physicist to know much about it. I haven't really followed up
Yeah, there's a lot of people working on it right now in the
Yeah,
valley.
absolutely.
All right, I think the time is up. Uh, um, so thank you all for attending this talk, and Alex, special thanks to you. Really intriguing topic.
Thank you, and thank you everybody for listening.
Yes, and we'll keep in touch. Thank you very much.
Okay, great.
And
Thank
see
you.
you all in 2 weeks from now.
Okay, thank you very
Yeah.
much. Bye-bye.
Bye bye.
Good. Bye-bye.